Thanks a lot. I would like to begin by thanking the organizers for organizing this wonderful conference and drawing in people from various different fields. It's my first time that I'm in ICTS, so Rajesh's introduction yesterday was useful for me. Right. So with that, I'll go directly into the title of the talk, which is Efficient Quantum Field Theories for Quantum Computers. Quantum field theories, we all know what they are. What do I mean by efficient quantum field theories become relevant in the context of what are we using the quantum field theories for? And in this context, we'll be using quantum field theories to make or to propose computations in quantum computers. Now, I will not give a very detailed explanation about quantum computers. We have the ideas in our mind about analog quantum simulations, digital quantum simulations, right? Simulators. So the idea here is in this talk would be to explore the various theoretical formulations that some of them exist and some of them are in the process of being developed, which would likely give us an advantage when we want to do the calculations on quantum computers as and when they become available. So that's the premise of the talk. So the work on which I speak about at length was done with these collaborators. So Sandeep is my PhD student who's about to graduate. He was the main driver of the work. So most of the results that you see are figures prepared by him. And then this was also done in collaboration with Shailesh Chandrasekharan, who's at Duke. I believe he visits ICTS fairly regularly, so some of you know him. And this is Marina Marinkovic, she's at ETH Zurich. Now the plan of the talk is the following. We'll start by recalling a little bit about how QFT has encountered technology in the past few decades and how this has helped both fields. And then we'll talk about the new formulations that we have been investigating, the qubit regularizations, what are the models, and what is the speciality of these models. And I use the word magic. It is not at all meant to be a technical term, which I think will come in the next talk, but this magic is the pure curiosity of or lack of understanding that we have still about certain features of this qubit regularization, and they need more investigation, right? So this is a completely non-technical magic I'm talking about. And then depending upon how much time we have, we'll talk a bit more about Q dates and quantum links, which are the ways to talk about gauge theories in the problem. So the first part is essentially about scalar field theories and spin models and so on. And finally, we'll conclude. Right. So whenever you start asking about quantum field theories and how they have contributed to our understanding of the nature, the first example that comes up is quantum electrodynamics, the theory of the field theory, which describes how light and matter have interact with each other, right? And this has been extremely crucial for what started off as a theoretical curiosity in trying to understand the workings of the nature has turned out to be enormously beneficial for technology, right? We know that these investigations started more than 100 years back, starting from the experiments of Millikan and theories of photoelectric effect by Einstein, and then it has continued into the quantum theory of molecules, the various quantum theory of atoms, molecules, condensed matter, and so on. And this has really spawned and created new domains, right? You have domains like quantum optics, domains like quantum chemistry, material science, which has benefited so much to technology that we understand it as of now. And moreover, all these milestones that you see are various Nobel Prizes associated with this theory, directly or indirectly, right? What is so remarkable about this is that initially, at least when the theory was conceived, one did not need too many things to get started on calculating observables, right? Things you could match with in experiments. You really had a few set of interactions, how electrons would scatter from each other, how electrons would interact with protons by exchange of photons and so on. And initially, like in the 50s and the 60s, most of these calculations were driven by weak coupling methods, right? Perturbation theory, for which essentially all one needed was pen and paper. This is the quintessential characterization of a theoretical physicist. And it did go a long way. It did go a long way in the sense that people could compute physical values of the muon G-2 and so on, which could be compared with experiments and impressive accuracy. However, things changed when you come to the 70s and people started discovering you already had a lot of these particles like mesons and hadrons, but people started discovering a lot of them. And it quickly became clear that the microscopic theory in this context is the theory of quantum chromodynamics, QCD, which postulates the existence of microscopic particles called quarks and gluons, which, however, you don't see in nature because they are permanently confined inside other objects like baryons or mesons. So baryons have 3 quarks, mesons have a quark and an antiquark, and these are the objects that you see in the everyday world around us. Now, for this theory, it's highly interacting, right? And there is no easy way of performing any weak coupling analysis on this. So the development, the ab initio development of this theory essentially started in the 70s after Wilson taught us how to formulate these gauge theories on a lattice, on a space-time lattice, and then perform numerical Monte Carlo methods in order to calculate correlation functions, right? So since then, this has undergone a major revolution, and this revolution has been largely through HPC classical computing, right? The supercomputers of today's world that we see have been influenced by early lattice QCD calculations. Many of the Crays and the Blue Gene computers that were around, the architectures of many of these machines were driven by how you had to compute correlation functions of these physical hadronic correlators and so on. So this was one of the first examples where technology had benefited physics and vice versa, right? So in fact, this theory can go far more. So this is the figure that I have, which essentially shows you that taking 2 inputs like the mass of the pion and the kaon, these are the two theoretical inputs you take, you can compute the mass of an entire range of strongly interacting particles, right? And these points are the results from lattice QCD. These bars are results from experiment, and they show a very good agreement. So in fact, you can also compute what is called the running coupling, and you show that the coupling really becomes strong as you decrease in energy, and therefore, for strong couplings, you cannot do perturbation theory, and this is a natural consistency with the fact that perturbation theory doesn't work, confinement sets in. So in fact, there are more interesting features that QCD predicts in that if you take your familiar matter around us and you heat it up to some trillions of degrees Celsius, you get a new phase of matter, the quarks and the gluons, in which the quarks are not bound inside a particular baryon or a particular meson, but they become properties of the entire medium. So that's what is called the quark-gluon plasma, right? Now, as we enter the 2000s, we stand at hopefully at the beginning of another technological revolution, where quantum computers and quantum simulators are becoming increasingly accessible to us as theoretical physicists, because experimentalists have a precise control of the quantum degrees of freedom, and they can potentially revolutionize the computing paradigm. So there are a host of devices, architectures that are available, starting from ion traps, optical lattices, superconducting qubits, and there is an intense research on trying to see which algorithm works better on which setup and so on. So this is like another developing field. I do mention that the experiments with ion traps and Rydberg atoms have demonstrated significant progress, especially for realizing constraint gauge theories. This is probably something I'll refer to the end of my talk if time permits. Now, one of the key features which drives us to look for new theoretical formulations is the following: that when experimentalists have these quantum systems under their control, they need a very precise control on a few quantum states, right? These quantum states can be 2, 3, 5, 10, 21, but hopefully not 10,000, hopefully not 20,000 and so on. Because the more number of states you have, the more difficult it is to control them very precisely, from what I understand. So the idea from the theoretical point of view is to have novel theory formulations which work on finite dimensional local Hilbert spaces and yet try to recover the same physics that we typically get from quantum field theories. Because quantum field theories, the way we learn them, have infinite dimensional Hilbert spaces. And that's exactly what we are trying to escape from, but still get the relevant physics under control. And so in this endeavor, we are, of course, we have a lot of lights, from various lighthouses, and one of the standing beacon is ideas of renormalization group. This is again Wilson in the 70s, who kind of the understanding of physicists like Wilson, Fisher, Kadanoff, and so on, tells us that we don't, if you want to reach a particular fixed point, which is quantum field theory, you do not need to search aimlessly. There is a very well-defined way of constructing microscopic models motivated by symmetries. And once you construct some, the model with the relevant symmetry, you can tune some bare couplings in the model and find a point or a region in your phase diagram where you have a phase transition, a quantum critical point, and you might have your way of formulating the theory. So this is what I call traditional lattice model. This is what lattice QFT typically does. It finds a quantum critical point at some point here, but someone else can come up with a completely different microscopic regularization by having the same symmetries and hit the critical point at a completely different different region, and then you flow to the same low energy physics that you are interested in. So this is the QFT you are looking at. Okay, so this is the idea that we are going for, and this is also so these lattice gauge theories. So the aim is to apply these ideas not only to scalar fields but also to lattice gauge theories. And in fact, in this endeavor, which I'm not sure how much I'll have time to talk about, condensed matter physics fits in very naturally, because there are certain aspects in condensed matter physics, notably that of frustrated magnetism, where you need very crucially the same ideas that are essential in particle physics, the ideas of spontaneous symmetry breaking, emergent gauge fields, and fractional excitations, right? So, so this is exactly the kind of phenomena in condensed matter physics that can also be targeted when you have such Hamiltonians, or qubit Hamiltonians or quantum link Hamiltonians at your disposal, and try and develop better computing methods to get observables for those, right? So that's also the area of impact. So after this introduction, I'll just go on to a bit more specifics. So, right. So let's just convince ourselves of something extremely pedantic, something extremely we are all familiar with, the example of a real scalar field theory. Right? So real scalar field theory has this momentum term. We already heard a lot about scalar field theory yesterday, so I'll not put in too much, excepting that this is the you have a gradient of the field phi. So phi is a field and pi is a momentum. You have a mass term and you have a self-interaction term like phi to the 4. You can rewrite this slightly differently, like this. It looks very intuitive in this form because this looks almost like an Ising model, excepting that these phi's are real numbers. So you have phi at site I, site x plus I, and kappa is a hopping parameter, and these are the self-interaction terms, right? And of course, phi and pi satisfy the usual commutation relations, but phi and pi, these are infinite dimensional operators. So if you wish, these are they are the Fock spaces of harmonic oscillators, and harmonic oscillators have infinite occupation numbers. So the local Hilbert space at each point is infinite dimensional, right? And this theory has been extremely well studied, both theoretically, analytically, and numerically. A very generic phase diagram of this model, having only n kappa and having only the parameters kappa and lambda is the following. So for small values of kappa, you have a massive phase or a paramagnet, and if you increase kappa, then at some point you have a phase transition and you go into the phase where the Z2 symmetry of this model spontaneously breaks, and you have the broken phase over here, the spontaneous symmetry broken phase here, and this is lambda. So you can increase the self-coupling a lot. So when lambda goes to infinity, you essentially go to the Ising limit, where phi can take values only +1 and -1, and that's really the Ising model, right? Right. So this is something that we know how at least the phase structure is very well known. Now, if you wanted to do this using a qubit regularized theory, again, this is something that we all know. I'll just repeat it just for the sake of being pedantic. So instead of having an infinite dimensional Hilbert space, you truncate your operator, you truncate a Hamiltonian by using projectors, right? So these projectors now project the operators x and p to the dimension, Hilbert space dimension that you're interested in. And in this case, I will just choose a two-dimensional Hilbert space, right? So it has only zeros and ones. And then the modified kinetic term just looks like this. So you have a hopping, but the hopping is now with this phi superscript q operators, right? And if I'm only working with two dimensions, right, a local two-dimensional Hilbert space, then the choice of these operators are very restricted. These have to be some sort of Pauli matrices. And I've chosen I've chosen the phi, the field phi, to be sigma 1 and the pi to be sigma 2. So if you substitute this, you simply see that the kinetic term just becomes pi 1 at sigma 1 at x and sigma 1 at site x plus I. So this is just the hopping term. And the rest of the terms are just constant. So essentially they drop out of the problem. So the Hamiltonian only with this term, only with this first term, at zero temperature would exist in a spontaneous, would exist in a Z2 broken symmetry. So the first thing to note is that the Hamiltonian that you get also has the same symmetry as the previous scalar field. So the Z2 symmetry in the original model was phi going to minus phi, pi going to minus phi. You have the same symmetries in the qubit model. You can realize them with this operator. And you can easily check that the Hamiltonian is invariant under the symmetry. But without any H term, right? So if you just have the first term, then you are in this phase. So you are in the phase where the Z2 symmetry is spontaneously broken. But however, if you add this extra term H, then you have a phase transition and you come out of the broken phase into the symmetric phase. So this is the very familiar example of the transverse field Ising model. I've just written it, you make a rotation on the spins and you get the TFIM. And it's the same, the phase transition in the TFIM is the same universality class as the real scalar field theory. This is well known, well established, nothing new here. Okay. Right. So next we do a slightly more challenging problem, namely asymptotically free theories, right? So asymptotically free theories, so asymptotic freedom is something that we saw in QCD. Whenever your energy scales are very high, very large, then the quarks and gluons are essentially free. They behave like free particles. But however, when your energy scales are very low, then these quarks and gluons are confined in hadrons, right? So you have you have a length scale coming up, which clearly separates the low energy physics from the high energy physics, right? And naturally, you want to understand whether of course, this phenomena also comes up in scalar field theories or spin models, right? And one of the very quintessential example is the two-dimensional O3 model, right? So why do we like asymptotically free theories? It's because these asymptotically free theories give us rich phenomenology with very few parameters. Because whenever you're in the low energy regime, you can form various bound states. These bound states have different binding, and this is exactly what happens in QCD, for example. You have quark masses, quarks form various bound states, and they have a very rich nuclear physics and so on. So 2D03 model is a very toy model of this asymptotic freedom. And in this model, so the aim of the next few slides is to just tell you how asymptotic freedom works with the 2D03 model, right? But remember, the 2D03 model is a quantum field theory, so it will again have an infinite dimensional Hilbert space. The idea then would be to find a qubit regularization with a finite number of states which reproduces the same physics, right? So that's what we'll. Right, so the action is extremely simple. So you just have unit vectors, right? So E is a unit vector, 3 components, but mod of E is 1. The action is extremely simple. You have a single Baire coupling, G squared. We know that in the QFT, the couplings flow. So if you have G squared, define it as scale mu, the beta function looks like this. And the negative sign is very important because this tells you when G squared is small, the flow would be such that it directs you to G squared equal to 0, right? So essentially, so the stable fixed point is that of a free field theory. So this is the first statement. However, if your G square is very large, then you are in the infrared, and then there is if your mu square is very large, if your mu square, I'm sorry, the other way around. So this is the free field limit, and if you go in the infrared, right, then what happens is that, so this is the next statement, in the infrared, the coupling will start growing, and because of the coupling grows, a mass gap will develop, right? And this is exactly what you can start seeing this if you integrate these equations of, you can just take the first term and you integrate it, and you see that you develop a mass gap which is inverse of this correlation length, and this mass gap is exponentially sensitive to the bare coupling. So this is exponential 2 pi by g squared. So if your g squared is small, your xi is very large, is exponentially large. Whereas if your g square is of order 1, then xi is again of order 1. This is the physics here. And this lambda is the scale that the theory has generated. So this will be the lambda parameter in QCD, or just the scale that separates the low energy physics from the high energy physics. Great. So far so good. Now the question is, if I want to track the renormalization group flow of this theory, how do I do this? Right? So and especially I'm thinking in terms of doing a calculation on the lattice using a lattice quantum field theory setup. So the idea is to compute mass gaps, because mass gaps are something that can be computed very well using lattice quantum field theory methods. So you can do your calculations entirely in Euclidean space. And in Euclidean space, of course, when you do your calculations, remember we are restricted to a finite box. The box is not infinite. However, you have a box size, and the box size will be called as L. So whatever mass gaps you compute, these are mass gaps in a finite box. That's why I call this M of L. So the mass gap is inverse correlation length. But what you're interested in is the correlation length or the inverse mass gap when the box size goes to infinity, right? L goes to infinity. So you have to be careful to take this limit all the time. The first thing you can do is that, the mu is an abstract quantity. It's some scale, right? So some experimentalists might be doing the energies, collider experiments, it's some energy scales, and that's the scale they measure the coupling constant in. Fine, great. We can do the calculation on the lattice. So what you do is that you have the box size, which is a scale. So box size is a length. So inverse of that length is an energy. So you can rewrite this entire beta function in terms of L. It's a completely valid procedure. So you do that, and then you get this expression. But however, you have this issue that you have a DDL over here. So essentially, when you're doing lattice calculations, you are changing the box sizes by the number of lattice points. So you have lattice of let's say size 2 cube, 3, 2 square, 3 square, 4 square, and so on. What I mean to say is that the number of points will change discretely and not continuously, right? So what is the way around it? The way around it is simple, is that instead of looking at the differential version of the beta function, you look at the integrated version of the beta function. So you integrate this, and this is exactly what is called the step scaling function. The step scaling function formally can be defined like this. You take the beta function, integrate it from a length scale L to another length scale S times L. So now you make the claim that I don't have to increase my length infinitesimally, but rather I increase my length of the box, or the size of the box, in finite amounts. So L, 2L, 3L, 4L, and 5, and so on, right? So in fact, this entire exercise can be done in perturbation theory when S is very small, and one can check that certain rigorous limits are obtained. But I'm going to skip that. Yeah. Yes. So we will forego this calculation completely. So I'm just saying that the idea is important, that you can define this step scaling function, and you can show that the step scaling function has a well-defined perturbative behavior. But when we do the calculation, we will do the calculation entirely in terms of the mass gaps. That's all. Yeah, and we'll define couplings accordingly. Right. So before we tell you how we do the calculation, essentially let's just understand a little bit about how the step scaling behaves. So first of all, for this particular asymptotically free theory, we saw that when g square becomes small, your correlation function diverges exponentially. Right? So therefore, this expression, if you wanted to look at so first of all, you want to form a dimensionless quantity on the lattice, because that's the really honest thing that you can honestly measure, because you don't have a physical unit of, you don't have a physical measure of what the lattice spacing is. It doesn't make sense for the lattice box. So you form this dimensionless quantity, xi of L by L, and you see that when L goes to 0, right, xi of L by L will go to infinity because xi of L diverges exponentially. So therefore, this will go to infinity. On the other hand, at low energies, right, which means when the box size is very big, your correlation function is only a few lattice spacings big. So this means that whatever excitation that you are creating can fit very well in the box, and therefore xi of L by L will go to 0 because L goes to 0, whereas xi of L remains finite. So, so all this is so far so good. So this is a, if you wish, this is a renormalized quantity because I'm only measuring inverse of the mass gap, which is the spectrum of the transfer matrix. However, so this is one of the quantities. The other quantities, what we can do is that we can measure the ratios of correlation lengths. So then you ask the question, okay, I have my box, I have my particle which I fixed, theory which I put it in a box, and there is this excitation. What happens to the correlation length if I increase the box size by a factor of s, right? So imagine if the particle is already massive and the box is very big, then nothing will happen, right? You have a particle whose Compton wavelength is let's say 3 Fermi, and you make the box which is like 300 Fermi. You increase the box size from 300 Fermi to 400 Fermi. Nothing will happen because it's a finite, it's a massive particle. It doesn't see the edges of the box. So this is the limit. This is the IR limit. On the other hand, if your particle is massless, then the maximal correlation length you can measure in a box is the size of the box, not more. However, if you increase the size of the box, then the particle realizes that it's still massless, and the correlation length increases. So therefore, if you try looking at the ratio of the correlation length, xi of s times L divided by xi of L, it will asymptote to this constant number s. And that's exactly what you can track on the lattice. So you kind of forego completely the measurement of beta function. Instead, you characterize running couplings. So this is a dimensionless coupling, right? This is another dimensionless coupling, and you start tracking how these two quantities behave with respect to each other. So in fact, if you take the traditional O3 model, which I showed you in this example, you discretize it on the lattice, and you compute this calculation, which was done by a bunch of people in the late 80s and early 90s, but this result is from an Italian group, Caracciolo, Edward, Sokal, also partly based in the US, where they looked at the step scaling function, and the step scaling function for the O3 model shows this behavior. So in the IR, it goes to unity, as we said it should, and in the UV, it asymptotes to the value 2, because we are looking at the two-step scaling function. S is 2 here, right? On the intermediate scale, of course, this entire thing is fully non-perturbative. You don't have an analytic control over what is going on. So you rely, so this curve is from a lattice calculation of the physics, right? And of course, the statement is that if you want to realize a different cubitized theory, which will follow the traditional O3 model, we expect it to reproduce this step scaling function, because the step scaling function essentially tracks how the RG, tracks the physics of the O3 model as you change the scales from the UV to the IR, right? However, I do want to point out that especially for these problems, it's quite challenging, because you have a lattice, because of course you have two scales, remember the UV and the IR, because you have the scale lambda that separates the IR physics from the UV physics, but in addition you also have the lattice spacing, and the lattice spacing is a source of all sorts of non-universal physics, which you want to disentangle. So this is a multi-scale problem, and these are always challenging problems in the lattice. So for the cubitized O3 model, a realization was found by these people around the same time when we were working in the problem. So what they did was the following. So they had what they call, I think they call this a Heisenberg comb. So they had a chain. So this is the Heisenberg chain with a coupling J, antiferromagnetic coupling J, right? And in addition to this chain, they put another set of qubits, so just spin halves, which are interacting with interacting with the first chain, but not with each other. So you have a coupling JP, with each element of the chain, but there's no coupling here, right? So JP was set to 1, and they investigated the physics, as you take J to infinity. How they came to this model is sufficiently complicated, and I can tell you later if you're interested. But for the moment, let's just look at the physics of it. So essentially, remember, you have one scale. You just put JP equal to 1, and you keep increasing J, and you just take bigger and bigger lattices. And let's see what happens. So this is the step scaling function from the standard SO3, from the traditional O3 model, which people knew. The dashed line is a result from perturbation theory. So you know that perturbation theory works well at very high energies, but fails at low energies. So these two curves match very well at high energies, but fail at low energies. Conventional wisdom. Now, when you start looking at what happens, from the lattice model, the qubit regularized model, you see that as you increase J, right? So for small values of J, you reproduce the IR physics sufficiently well. So you have some, so this is increasing lattices. Oops, sorry, I pressed the wrong button. Yeah. So you have small lattices, and you keep measuring the step scaling function on lattice sizes bigger and bigger, and at the same time you keep taking J to infinity. For small lattices, you see that you can reproduce the UV physics quite well when J is small, right? So when J is 3, you can reproduce the lower part of the curve pretty well. You increase J, and then you have some. First of all, you have some lattice artifacts, which I promised you will be there anyway. So once you start getting rid of the lattice artifacts, you see that this curve, these points follow the curve at a higher energy scale, right? Or J equal to 5. And then as you keep increasing J even further, you reach the higher and higher energy scale, right? So for J equal to 10, you can reach the step scaling function curve already at very high energies. And once you have reached the curve, then you've already reached this scale, LUV scale, and then increasing the lattice size further will only flow you down to IR, and this is exactly what they saw. Okay, so this is one of the very nice demonstrations of a qubit O3 model, a qubit model giving the physics of the usual 2D O3 model. So we were kind of working in parallel, and we wanted to understand if qubit theories can do more, right? And one of the most obvious questions to ask is that, well, you have the 2D O3, but what about the 2D O2, which has the BKT phase transition? And this is exactly where we'll see some very nice results coming up. It's a very similar theory, excepting three component vectors. You have a 2-component vector, so the action looks pretty much the same. The physics is also extremely well understood. So you have a massive phase where you have only a few vortices, right? The vortices are bound in this phase. And then as you reach the BKT phase transition, you have a critical point where the correlation length diverges. That is the BKT phase transition. And then as you cross the phase transition, your vortices proliferate, right? This is the vortex unwinding transition, and you get into a critical phase, right? So in fact, there are many exact results known about this model. Close to the BKT phase transition, it is known that you can separate out the spin waves and the vortex part very clearly. And this is the Sine-Gordon model. So you can, you have a theta1 part of the field, which is only the spin wave. You have a theta2, which is only the vortex, and they satisfy, this is an exactly continuum field theory, and this field theory can be solved. It is integrable, or rather beta integrable, if I understand. So a lot of exact results are known about this, right? And this massive continuum theory is asymptotically free at this point, and this is exactly the physics we would try to reproduce with the qubit regularized theory. However, before we do that, let me just tell you a little bit about what challenges people have faced in the typical XY model, even though this has been studied for decades. So one of the things is that if you want to study the BKT phase transition, as those of you who are working with Monte Carlo would know, you would need to fine-tune yourself close to the critical point, right? And this is a very careful thing if you do, because the correlation length increases exponentially. So you need larger and larger lattices to kind of pin this down very carefully. So there have been some people who have been doing this extremely carefully, and Martin Hasenbusch at Berlin previously and at Heidelberg now has been doing this for a few decades. And one of the reliable estimates of beta C is this number 1.1199 with an error bar on the last digit. So even though you tune yourself to the critical point, it has been found that the observables that you compute have significantly large finite size corrections. And in fact, some of them are logarithms, which is what it makes it very difficult to estimate the, the thermodynamic limit. So a very common quantity that one computes in this, to locate the phase transition is the superfluid stiffness. So you have these vortex solutions, and you can get a current, and you look at the expectation value of the square of the charge of the current, and this is the superfluid stiffness. And this is exactly known what this number is. You can compute it from the Sine-Gordon model or perform this summation here. This number is like 0.636508 to very precise number. However, when people do these calculations on the lattice, so you see the results are from 1.1199, 1.1209, 2001. You see that this is the exact analytic value which you would have expected, but the values that you get are still far away. Now, of course, this is still like a 6-7% deviation, and you may not worry about that. But it's good to understand where exactly, or can this be understood? So it turns out that it is understood. There are large logarithmic corrections, but so once you take into account the logarithmic corrections, you can show that the value gets you reach this universal value, right? The y-axis is the superfluid stiffness. So this is just what I showed here. And on the L is the, right. So the other thing, notice that the size, right? The lattice size, so note the lattice size is almost like 1,000 by 1,000. And even then you don't, even then you still are very far away. Okay, great. So how does this help with the qubit formulation? So in the qubit regularization model, essentially you can take qubits, you can take, you take a model where you have a restricted Hilbert space. So in fact, each site has 4 states, and there is an easier way to think of the model. I will tell you this. So you can think of this model as a 2-layered dimer model, right? So you have just think of your classical dimer model that I'm sure you are all familiar with. You have a dimer model. You have a dimer model layer 1, dimer model layer 2, and now you can have 2 different couplings. One is a coupling in the in the same layer. You can place dimers. So this is this coupling. So in the field theory language, this is some sort of a current coupling. And then you have this lambda coupling, which is an instant-on coupling. This couples 2 different dimer, layers of the dimers to each other. Of course, this model has also been studied by many familiar collaborators, and results are known. But we are trying to study this model from a slightly different point of view. So it turns out that the physics of the asymptotic freedom does emerge, and the scenario is the following. So when you have, so the asymptotic freedom is reached in the limit where your lambda goes to 0 and L goes to infinity. So lambda is very small and your lattice is very big, but lambda is, it tends to 0. This is a very nice example where lambda equal to 0 and tending to 0, these 2 limits give you very different field theories. So when lambda equals 0, these 2 layers are not coupled at all, right? So you just have 2 layers of classical dimers existing by themselves, and these dimers have power law correlations. It was computed by Michael Fisher in the 60s. And so when you are sitting at lambda equal to 0, you essentially flow to this decoupled fixed point. That's it. However, if you have a tiny bit of lambda, then your theory doesn't, this is a repulsive fixed point, and you are no longer flowing to this fixed point. You end up flowing to the fixed point nearby, which reproduces the physics of the 2D03 model. So this is the scenario which is happening. I'll just convince you in the next 2 or 3 minutes that this is indeed what is happening. So again, what we do is that we compute the step scaling function. So the step scaling function, so the solid curve that you have over here is a result from the conventional bosonic, the standard 2D XY model. This is the curve, and then you see the behavior very similar to what we saw in the 2D03 model. So as you decrease lambda, you keep on accessing more and more in the UV regions, right? So for lambda equal to 0.6, you reach only this part of the curve, right? The entire IR up to medium high in the energy scale. As you go to lambda equal to 0.2, 0.4, 0.6, 0.4, 0.2, 0.01, you start reaching the higher and higher in the UV. And in fact, for 0.0, you can actually almost touch the UV fixed point. So this indeed reproduces the universal step scaling function. So that's a +1. This is something we knew, or at least you could expect based on what I showed you before. This is just showing the 4 figures separately. So lambda equal to 0.6, it touches here. So this gives you a way to estimate for you, the L UV, which I showed before. So the last 2 minutes are just to tell you So of course, this is something that happened in O3, and you would say, great, this is happening in O2, but what is the big deal? So the big deal that we noticed was that you have an enormous reduction of any finite size effects. In fact, it turns out that these logarithmic corrections are no longer there. So what are we looking at? So we're looking at the running coupling xi of L by L, which is a dimensionless quantity plotted as a function of L, right? And these two curves, these circles and these triangles, are the results that you get from the XY model, the standard XY model. And you see that even for very large lattices, up to 2560, they are still away from the dashed curve, which is what you expect for the UV fixed point. Whereas for the qubit model at 0.01, these are all finite size effects, but it reaches the universal value much before it reaches the universal value much before the traditional model does. And in fact, the same story gets repeated for superfluid stiffness, in the sense that this is the result for the decoupled model, lambda equal to 0. This is not so difficult. But if you look at the UV fixed point, you see that the results from the traditional model are still very far away, whereas the model from the qubit regularized model reaches this value already at a few hundred lattice sizes, something like 500 squared, right? So in fact, once you know how to work with the step scaling function, you can also compute the infinite volume correlation length. And again, you do know that you are sitting close to a BKT phase transition, so these correlation lengths would grow exponentially, and you try various the fit forms, which are exponential in 1 by lambda, and you see that when you add a small log correction, you can fit the infinite volume correlation length up to 5 orders in magnitude. So it's a very simple fit form, but it does reproduce the physics of the 2D03 model up to several orders of magnitude. Right? So I think this is a good point to stop. If you have questions, and if you're interested in more, I will tell you. I'm happy to catch up. Let's go to the conclusion.
Thank you, Debashish. Questions?
Yeah, Debashish, can you explain a bit more about the asymptotic freedom physics and the qubit formation in your...
Yeah. Sorry. So what happens is the following, is that, let me go to this figure. Yeah, right. So here what happens, so what happens with asymptotic freedom is that if you go to, so you have, your energy scales at which you are doing, let's say you're doing some scattering experiments, and if you go to very large energies, right, then you are probing very short distance scales. And essentially if you go to very large energies, you're asking the question at very short distances, whatever the particles in the theory are, how strongly interacting are they? And as we see, both in the case of QCD and in the case of 2D03 model, if you go to very high energies, these excitations, these are free at very high energies. Now, the very shape of the very nature of the beta function tells you that if you now come away from very high energies to lower and lower energies, then the coupling constant will start growing. Now, if the coupling constant starts growing, then there is a possibility that these, whatever basic particles you have, starts interacting and forming some sort of bound states. Okay. So in fact, in QCD, this ties in very nicely, because as you go to lower energies, you also encounter confinement, and all these particles are confined in a single. You get
this. I mean, the quarks can make some qubit.
Yes, qubits, right.
And the model that you described, O3 model, that falls with the same universality class of the...
So the 2D O3 and 2D O2 are different universality class. So what happens in the 2D, again, just to very quickly, so what happens in the 2D, sorry, I'm going in the wrong direction. So what happens in the 2D O3 is that your xi of L by L can increase as much as you want it to. But in the case of the O2 model, what happens is that you encounter, you have this phase transition at some point. So the x-axis cannot go, beyond a certain point. So therefore, when you look at the step scaling function, you are a kind of hit over here, right? And the other good thing, just to emphasize this once again, is that when you are trying to reach this BKT phase transition in the traditional XY model, you really have to tune beta. You say that, well, I have to find out beta c by some finite size scaling of susceptibility, a specific or whatnot, and I have to sit at beta c close, as well I can manage to get that physics. However, in this way of looking at it, right, in the way we have formulated it, it's far easier because you don't really have to tune lambda. All you have to say is that lambda is small. It's just close to 0. So this 0 could be 0.01, it could be 0.02, it could be 0.015, one doesn't care. You will still get the physics of the BKT phase transition. So in some sense, you're solving a fine-tuning problem.
We should.
So if you consider the 1D Heisenberg model with bond dimerization,
Yeah.
you get the effective O3 nonlinear sigma model, but with a theta term.
Yes, that's right.
And both the coupling constant and the theta flow under RG.
Yes,
I was wondering whether you have seen how they...
In fact, there is a qubit regularization which tries to do that. So they try to look at the, so I think they do it slightly differently. There's this notion of, yeah, I don't remember the details, but we can chat later. So we don't see that. I mean, we have not studied that, but there are people in the community who studied exactly that using qubit regularization.
I mean, the qubit regularization is exactly what I said, just nonlinear Heisenberg model with bond dimerization.
Absolutely, yeah.
Then I think if you want to see asymptotic freedom, it's efficient to add legs.
You add legs.
Right.
Yeah, Manik.
Naive question. So at the starting of your talk, you mentioned that this local Hilbert space.
Right.
What does that mean?
So this means that if you are working on the usual, the scalar field, right, the Hilbert space is that of a harmonic oscillator. The Fox space that you built up is the Hilbert space for harmonic oscillator.
Particular this term local.
Local means that your field theory is extended in space, but however you are looking at each point.
So in space time it is some localized.
It's a local. So I'm defining this phi at a site. At a site.
So now in the space time structure, what is the volume? Any restriction or that kind of thing?
So in this case, so this of course depends upon what quantum degrees of freedom you are using, right? So if I'm using harmonic oscillators like I do in scalar field, this is infinite dimensional. But you can also use quantum rotors and quantum spheres, which Rajdeep did in his talk yesterday, and that's also an infinite dimensional space because a quantum rotor has an infinite, infinite excitation, L equal to 0, plus minus 1, plus minus 2, and so on. So here what we are doing differently is that we are saying that you do not have an infinite dimensional Hilbert space. You really have a space of a qubit or a qdate or whatnot.
So if you have a site A and site B, the total Hilbert space is HA tensor H.
Yes,
So this
yes,
tensor product
that you have.
Any other questions? So Debashish, do you have any physical insight into why the qubit regularized models show better finite size scaling or properties? Or
Actually, that knows. So that's the why we say magic. But there are some ways of, so it is known in the literature, people have studied what are called topological actions, in the sense that you can take, your favorite O2 or O3 model and whatnot. And as I wrote down, right, the O2 model is just a cosine of theta x minus theta of x minus I, x plus I. And there's another way of writing these models. It says that your action is this action if the angular difference is below some critical value theta c angle. But if it's infinity, if it is above a certain theta c. So this is topological action in the sense that you do not allow angular deformations from side to side beyond a certain theta c. And those models are also known to have very small cutoff effects. So we don't know exactly the relationship between these qubit models with those models, but this is a hope to understand this in the future.
Okay. Are there any other? If not, let's thank Debashish once again.
Thank you for your question and attention.
We will move to the next talk. The next talk will be by Marcello Del Monte.